Alright guys, welcome to chapter 7. This is the video for your fill-in notes. Here you see the learning objectives. In this chapter we're going to look at gases, measuring pressure of gases and convert from one unit to another. You'll be able to describe the relationship between pressure, volume, and temperature of a gas using gas laws. You will describe the relationship between volume and the number of moles of a gas. You will also be able to write the equation for the ideal gas law and use that equation for calculations. And lastly, you will be able to use Dalton's law to determine the partial pressure and total pressure of a gas mixture. And so we start off with the 3 states of matter, which is something that you've learned a long time ago. This table summarizes the properties of gases and liquids and solids. And so you can take a look at this and study this. You need to be able to obviously tell the difference between gases, liquids, and solids. And notice that we have listed here several different properties. The first one being shape and volume. Next there is the arrangement of particles. And then a little bit about density. Remember, density is the ratio of mass to volume. And next we have particle movement. And then lastly we have interaction between particles. So this is a very good chart to just summarize the different states of matter and their properties. So be sure and study this chart. And so if we look at looking at the states of matter just a little bit more, we see that we have the 3 states of matter, particle drawings of the 3 states of matter. And the reason that a substance exists as either a gas or a liquid or a solid depends on, first of all, the balance between the kinetic energy of its particles. So it does depend on energy, and so gases have the most energy between their particles and solids have the least. Another important part to what state of matter a substance is depends on the strength of the interactions between the particles. The strength of the interactions between the particles. So we'll spend some time looking at those interactions as we move through. There is something called the kinetic molecular theory of gases, and so this is the KMT for short, kinetic molecular theory. And this is a scientific theory that explains why gases behave the way that they do. And so there's several parts to this kinetic molecular theory, and this slide is listing those parts. So first of all, gases consist of particles that move both randomly and rapidly. So gas particles are in constant motion. They are simply going to move in a direction until they hit something, and then they will turn and go a different direction. And they move very rapidly. They have a lot of kinetic energy. The next point to this kinetic molecular theory says that the size of gas particles is small. So the individual particles themselves are small compared to the space between the particles. So we know that gases will fill the container that they are in and typically have a lot of space between individual molecules. So because that space is so great, the actual size of the gas particle itself is very small in relationship to that. So sometimes we say that the size of the individual gas particles really doesn't matter. Next it says gas particles exert no attractive force on each other. Gas particles exert no attractive forces on each other. The next part of the theory says that the kinetic energy of gas particles increases with increasing temperature. So we see a direct relationship there. As the kinetic energy goes up, the temperature goes up as well. And then lastly, when gas particles collide with each other or with the side of the container, they will rebound and go the opposite direction. So this kinetic molecular theory is used to describe how what's called an ideal gas behaves. And an ideal gas is just what it sounds like. It's a perfect gas in a perfect world. If you had a perfect gas, it would behave according to these statements that we've just gone over, the kinetic molecular theory. We study ideal gases and we can learn about them, all the different variables that we can measure, and how to use gas laws to manipulate those. And then we'll take a look at real gases and how similar or how different they are from the ideal gas. There's actually 4 variables that you can measure for a gas. The first one is the volume. We can measure the volume of a gas. And remember, volume is the amount of space that the gas occupies. And for gases, this depends on the container that it is in. And so to measure the volume of a gas, you would simply measure the container that is holding the gas, because the gas is going to fill the container completely. The second variable that we can measure is the temperature of a gas. A temperature is a measure of the average kinetic energy of that sample. And so when you put a thermometer in a sample, it's measuring average kinetic energy. The next variable that we can measure is something called pressure. Pressure is simply a measure of the force that the gas exerts on the walls of the container. And so every time the gas particle hits the side of the container, that applies force to the side of the container, and that can be measured. And lastly, we can measure moles of a gas. And mole is just a unit that tells us how much of the gas we have. It measures the amount. All right, our next slide is showing us some different gas pressures. And so for whatever reason, people use different units for gas pressures. And you need to be able to convert between those units. The most commonly used pressure unit is atmosphere. And so then we see all of these other 4 units that we have here and how they're related to 1 atmosphere. So 1 atmosphere is equal to 760 millimeters of mercury. It's also equal to 760 torr. 1 atmosphere is equal to 14.7 psi. PSI stands for pounds per square inch. Pounds per square inch, PSI. And it also is equivalent to 101,325 Pascal. PA stands for Pascal. This is named after a physicist, Blaise Pascal. And this is actually the metric unit for pressure, a Pascal. All right, so I want to just go through a couple of examples of how to convert between pressure units. And so in the first example problem we see here, it says 840 torr is equal to how many atmospheres? So we're going to use unit conversions to help us convert between the units. And so we always start with what we were given. So 840 torr. We're going to multiply that by a conversion factor. And so these are our conversion factors. These things that we just went over, we're going to use those as conversion factors. So since we want atmosphere, we need the conversion factor that has both atmosphere and torr. And so we see that 1 atmosphere is equal to 760 torr. There's a little decimal here just to show precision. And we know that this is set up correctly because we see that the unit torr cancels. And so when we do this math, we'll end up with the unit atmosphere. And so if you put this in a calculator, 840 torr divided by 760 torr is equal to 1.1 atmospheres. Our answer needs 2 significant figures because the given number has 2 significant figures. So 1.1 atmosphere would be our answer. Here's the second example problem. We have 2.059 atmosphere equals how many Pascal? And so again, we would start with our given. We're going to multiply that by conversion factor. Now we want our conversion factor to have atmosphere on the bottom because we need it to cancel. So we know that 1 atmosphere is equal to 1,001,325 Pascal. And so just to make sure that our atmospheres cancel, so 2.059 times 101,325 is equal to 208,600 Pascal. If we check our significant figures, we see that we have 4 sig figs in our problem and we have 4 sig figs in our answer. So that would be correct. So you will get the chance to practice some more of these types of problems this week. And so hopefully this was helpful. We want to briefly go through the different gas laws and see how they relate some of these different variables to each other. And so we're going to start that journey with something called Boyle's Law. Robert Boyle was a scientist and he studied gases. And Boyle's Law focuses on pressure and volume. It says for a fixed amount of gas at constant temperature, the pressure and the volume of a gas are inversely related. So inversely related means that when one of these variables increase, the other will decrease. So if one quantity increases, the other quantity will decrease, and vice versa is true. I didn't spell that right. Let's try that again. All right, that's better. So if one quantity increases, the other quantity will decrease, and vice versa. Here we see an equation. It says that the product of the two quantities is a constant that we call K. And so K, as you see here, pressure times volume equals K. K is just a constant. And so that shows us that pressure and volume are inversely proportional. Let's look at an example using Boyle's Law. So we have both words and a picture to kind of help us make sense of this. And so it says if the volume of a cylinder of gas is cut in half, the pressure of the gas inside the cylinder doubles. So in this case, the volume went down and the pressure went up by the same margin. And so we can see in our picture here that this is a container with a piston that moves up and down. And so in the first container, we have a pressure of 1 atmosphere and a volume of 2 liters. But when we take this piston and we push down on it, that makes our volume go down to 1 liter, and we can see that the pressure increased to 2 liters. And so there is an equation that we can use to help us calculate the new pressure or the new volume, the new condition. And so it is here, pressure 1 times volume 1, these are our initial conditions, is equal to pressure 2 and volume 2 of our new conditions. So let's try out a problem using our new equation here. So here's an example. It says if a 4-liter container of helium gas has a pressure of 10 atmospheres, what pressure does the gas exert if the volume is increased to 6? And so the first thing we want to do anytime we have a word problem is to pick out what has been given to us and what we're trying to solve for. And so as we read through the problem, we can see some numbers and their units. And so the first one we have is 4 liters. I know that liter is a unit of volume, so I'm going to call that V1, 4 liters. If we keep reading, it says that this helium sample has a pressure of 10 atmospheres. So I'm going to add that to my list. Next it says what pressure, so it wants us to solve for P2, does the gas exert if the volume is increased to 6 liters? And so before we start doing the math, we should ask ourselves, what do we expect to happen? So we see that from volume 1 to volume 2, the volume increased. The volume went up. And so what will happen to the pressure? We know that the pressure and volume are inversely proportional, so if the volume goes up, the pressure should go down. And so when we get our answer, it should be less than 10 atmospheres. So that's a good way to check your work. So step 2, we see we should write the equation and then rearrange it to isolate the desired quantity on one side. So I'm trying to solve for pressure 2. So I'm going to make a new equation by rearranging the existing equation so that I can solve for pressure 2. So I want pressure 2 equals, and notice that pressure 2 is on the right side of the equation. So I'm going to take everything on the left side and I'm just going to write it as it is. And then I'm going to need to get rid of V2. And in this equation, pressure and volume are being multiplied by each other. So if I simply divide both sides by V2, that will cancel V2. And so on the right side and on the left side, we would be left with P1 V1 over V2. So this would be my new equation. And once I have my equation, I'm ready to substitute in my numbers. So P2 is equal to 10 atmosphere times our volume 1, which is 4 liters, divided by our volume 2, which is 6 liters. Take a minute to cancel units, and so the only unit we have left is atmosphere, and that is the unit we would like to end up with. And so if I do my math, 10 times 4 is 40, divided by 6, 6.7 atmospheres. And so I would just double check and make sure that that is less than what we started with, and in fact it is. So that gives me some confidence in my answer, 6.7 atmospheres. Notice that I have 2 significant figures in my answer, and that is because of the numbers given in the problem. The least amount was 2 significant figures. So that would be the correct answer. Boyle's law is very applicable to the human body, and in fact that Boyle's law, this relationship between pressure and volume, is how we move air in and out of our lungs. And so these next 2 slides will show you how that happens. And so we start with inhalation, breathing in. So when we inhale air, the rib cage expands. And you can even feel that happening if you put your hands on your ribs and you breathe in. You can feel the rib cage expanding, and the diaphragm lowers. So here is the diaphragm right down here, and it is going to lower. As this happens, this increases the volume of the lungs. Increases the volume of the lungs. Well, as the volume increases, the pressure is going to decrease. And because the pressure is decreased, then air is drawn into the lungs to equalize that pressure. So it's more than just a matter of opening your mouth. Everything has to work together for air to be forced into your lungs. And so that is the process of taking air in. And now let's look at the process of exhaling air. How do we get rid of that air? And so to exhale air, the rib cage contracts and the diaphragm is raised. So notice in the first picture on the slide before that the diaphragm is pretty much straight across, where in the second picture, notice that there's a roundness to it. It's curved. And so the diaphragm is raised. This decreases the volume of the lungs. So there's not as much room in the lungs when the diaphragm is in this position. And decreasing the volume causes the pressure to increase. And air is expelled out of the lungs to equalize this pressure. So this is how Boyle's law relates to us breathing in the oxygen that we need. All right, let's move on to our second law. This is Charles's law. And Charles's law says, for a fixed amount of gas at a constant pressure, the volume of the gas is proportional to its Kelvin temperature. The volume of the gas is proportional, directly proportional to its Kelvin temperature. Let's add that word directly there. That's kind of important. Directly proportional to its Kelvin temperature. So directly proportional means that when one goes up, the other also goes up. So if one quantity increases, the other increases as well. So I think that's a blank that's covered here. If one quantity increases, the other increases as well. And so here we have a similar diagram to what we've seen before, but this time we're looking at volume and temperature. And so in the first picture, we see there's a volume of 1 liter, and the temperature is 200 Kelvin. Kelvin is another temperature scale that we'll look at in just a moment. We have degrees Celsius, we have degrees Fahrenheit, and there's also something called the Kelvin scale. And so if we increase this temperature to 400 Kelvin, we see that the volume increases to 2 liters. And this is an attempt to make sure that the pressure stays the same. So this is all at constant pressure. And so that just like before, there is an equation, and because these have a direct relationship, you see that it's written slightly different. We have volume 1 over temperature 1 is equal to volume 2 over temperature 2. And so we could use Charles's law to solve some problems like we did before. Charles's law is important in the explanation for wind currents. And so this graphic is explaining how wind is produced. And you can take a look at that and see how Charles's law is used to explain that. Our next law is Gay-Lussac's law. Gay-Lussac's law relates pressure and temperature. So his law says for a fixed amount of gas at a constant volume, the pressure of a gas is proportional to temperature. So Charles said the volume was proportional to temperature, and Gay-Lussac says that pressure is also proportional to temperature, as long as you have a constant volume. So if one quantity increases, the other increases as well. Increasing the temperature increases the kinetic energy of the gas. And you can abbreviate kinetic energy, capital K, capital E, kinetic energy. And so we see the diagram again. We have on the left-hand side a pressure of 1 atmosphere. Notice that the volume is 2 liters and the temperature is 200 Kelvin. And then on the other side we have a pressure of 2 atmospheres. The volume stayed the same, but the temperature increased. So the pressure increased and the temperature increased. And so here we see the relationship between pressure and temperature. This would be the before conditions, P1 over T1, and then the new conditions would be P2 over T2. So these 3 laws will be very important in gas calculations. We can also combine these 3 laws into something called the combined gas law. And so the combined gas law looks like this. P1V1 over T1 is equal to P2V2 over T2. This is what's called the combined gas law. Remember the P1, V1, those are your initial conditions. And then P2, V2, T2 are the new conditions. You can rearrange this formula so that you don't have fractions involved. In fact, I prefer this other arrangement. So it would be P1, V1, T2 is equal to P2, V2, T1. This rearrangement, you have to be very careful though, because notice that the temperatures have switched sides. And so this is, to me, a little bit easier to work with because I'm not a fan of fractions, but there is something to remember about the temperatures. Make sure you get those on the correct side. So it says this equation is used for determining the effect of changing 2 factors. So we could change both the pressure and the temperature and see what effect that might have on the new volume. And so you'll get some practice with those. In the next slide you have a summary of the 4 laws that we've just talked about. We have Boyle's law, Charles's law, Gay-Lussac's law, and then you see the combined gas law, which puts all 3 of those together. So maybe just this page right here, if you could have that handy while you're doing your practices, I think that would be very helpful. All right, let's talk about one more law, and it's called Avogadro's law. And Avogadro's law says that when the pressure and the temperature are held constant, then the volume of the gas is proportional to the number of moles present. So this is relating volume and moles. And so if one quantity increases, the other one will increase as well. That's what directly proportional means. So if the volume increases, the moles, or if the moles increases, the volume will also increase. So notice this time that we're keeping pressure and temperature constant. And so we have our cylinders again. We have a volume of 1 liter. We have 1 mole of sample. If we added another mole, so a total of 2 moles, in order to keep the pressure and the temperature constant, the volume would have to double as well. And so these 2 variables are related with this equation. Here's another important thing about Avogadro's law that it helps us with. It says often amounts of gas are compared at set standard conditions of temperature and pressure. And so this set standard of conditions is abbreviated STP, standard temperature and pressure, STP. Standard temperature and pressure. That's what STP stands for. And what are those conditions? So standard conditions are 1 atmosphere and 273 Kelvin. 273.15 Kelvin. K equals Kelvin, which is another temperature scale. And so because of these conditions at STP, Avogadro came up with this idea and tested it. Says that at STP, 1 mole of any gas, this is really important, as long as it's at STP, standard temperature and pressure, 1 mole of any gas has a volume of 22.4 liters. So 22.4 liters is called the standard molar volume. And so this allows us to have another way of converting to moles. And so we can see the example here. We have 2 balloons filled with different gases. The blue balloon is filled with nitrogen gas, and the pink balloon is filled with helium gas. We have standard conditions, 1 atmosphere and 273.15 Kelvin. And we can see that the volume is exactly the same, 22.4 liters. Now the masses are different. Nitrogen has a larger mass than helium, but the volume is exactly the same. All right, so how can we convert moles of a gas to volume at STP? Oh my goodness. I'm not sure what's happening down here. All right, so this example says how many moles are contained in 2.0 liters of nitrogen gas. 2.0 liters of nitrogen gas at standard temperature and pressure. So I always tell my students to put a smiley face when you see at standard temperature and pressure, because this allows for a very quick conversion. So let's follow the steps. In step 1, we want to identify the known quantities and the desired quantity. So what is it telling us? What information does it tell us, and what are we asked to solve for? So we know that we have 2.0 liters of nitrogen gas at STP. That's important. And we want to know how many moles that is. So that's our question mark. We want moles of nitrogen gas. And so we can write out 2 conversion factors. We're going to use those again. And so we know that because it's at standard temperature and pressure, we have 22.4 liters over 1 mole. Or we can put 1 mole on top and have 22.4 liters on the bottom. And so we want to choose the correct factor that would allow us to cancel liter. And so we want liters on the bottom. So we're going to set up our problem. We always start with our given amount, 2.0 liters of nitrogen gas. We're going to use the conversion factor that we've chosen. We put 1 mole over 22.4 liters. And I can just verify that this is the correct conversion factor because liter cancels. And so we see that 2 divided by 22.4 is equal to 0.089 mole of nitrogen gas. So that's a very quick way to calculate moles, as long as we have standard temperature and pressure. All right, lastly, let's talk about the ideal gas law. So the ideal gas law, a minute ago we talked about the fact that an ideal gas is like the perfect gas. I apologize for my notes here. I'm not sure why this is looking like this, but your copy looks clean. And so it says that all 4 properties of gases, that would be pressure, volume, moles, and temperature, can be combined into a single equation that we call the ideal gas law. And so the ideal gas law is written like this: pressure times volume is equal to moles times a constant that we call the gas constant, R, times temperature. And so we have PV equals nRT. In my AP chemistry class, we call this our Pivnert equation. That's just an easy way to remember what all the letters are, so Pivnert. Let's talk about this constant R. And so R is called the universal gas constant. And if you look at your numbers that you have written here, here's one of those. R is equal to 0.08206. Take a look at the units for this constant. We have liter times atmosphere over mole times Kelvin. And so this constant is just a number that allows us to cancel the units out that we need to cancel. So we want to make sure that when we're using the ideal gas law, that our variables have the right units, have the correct units. And so our volume has to be measured in liters. Our pressure has to be measured either in atmosphere, or we could choose this other constant if our pressure is measured in millimeter of mercury. And we want to make sure we have moles, and we also want to make sure that our temperature has been converted to Kelvin. And so these are the two gas constants that we work with. I use this one by far the most. I've used it so much that I have it memorized, so I hope that will be the case for you as well. All right, so let's look at an example problem here. It says, how many moles of gas are contained in a typical human breath that takes in 0.5 liters of air at 1 atmosphere pressure and 37 degrees Celsius? And so we want to make a list of all our variables. We have pressure, we have volume, we have temperature, and we have moles. And so I've listed those here. Those were all of the variables in our Pivnert equation. And as we go through the word problem, we want to pick out the number and its unit and put it in the correct place. So we can see from the very first few words, we are solving for moles. So I'm going to put my question mark there. My answer needs to be in moles. If we keep reading, we see that we have 0.5 liters. That is our volume, so 0.50 liters of air at 1 atmosphere. So that's our pressure, 1 atmosphere. And the temperature is 37 degrees Celsius. 37 degrees Celsius. If I take a look at all of the numbers that were given to me, I want to just take a look at significant figures. I noticed that pressure has 2 sig figs, volume has 2 sig figs, and temperature also has 2 sig figs. So that means our answer needs to have 2 sig figs. So I like to make myself a little note so I don't forget that. All right, step 2, it says make sure that all of the values are in proper units. So remember, we're using the gas constant R, and the gas constant R needed specific units. So we need liters, we need atmosphere, and we need Kelvin. And so I look at what was given. I have liter and I have atmosphere, but notice our temperature is in degrees Celsius. So we have to change 37 degrees Celsius into into Kelvin. And so in order to change Celsius to Kelvin, you add to 73.15 Kelvin to 73.15, and that changes your Celsius temperature to a Kelvin temperature. So when we do that math, we see we have 310 Kelvin. All right, so based on the pressure that we were given in atmosphere, we know that the R value that we're going to use is the 0.08206. And again, those units, liter atmosphere over mole Kelvin. And so we have everything we need now to solve our problem. We are solving for moles. So step 3 says to rearrange the equation to solve for moles. So N is moles. I want a new equation that says N equals. And so my mole is on the right side of the equation. I'm not changing anything on the left side, so I'm going to go ahead and write those down, P times V. And I need to get rid of the R and the T. So since they are being multiplied, I'm simply going to divide both sides by RT, and that will allow me to rearrange my equation to solve for moles. Now that we have our equation rearranged, we simply want to plug in our numbers. And so N is going to be equal to our pressure, which was 1 atmosphere, times our volume, which was 0.5 liters, divided by our R value, 0.08206 liter atmosphere mole Kelvin. And our new temperature in Kelvin was 310 Kelvin. So take a moment and make sure all the correct units cancel. So we have liter cancels with liter, atmosphere cancels with atmosphere, Kelvin cancels with Kelvin, and our unit mole is left, and that's exactly what we were trying to solve for. If we go back and look, we made mention that we needed 2 sig figs, so my answer is going to be rounded to 2 sig figs. We have 0.020 moles. When I put this in my calculator, I encourage you to grab your calculator right now, and let me just walk you through this. Sometimes it's a problem when there's 2 numbers on the bottom to divide by. So this is the easiest way that I've found. So if you'll turn the calculator on and just punch the numbers in as I say them. So you'll have 1 times 0.5 divided by 0.08206 divided by 310, enter. And that should have given you this answer. You may have to round it to the correct number of sig figs. If you didn't quite get that answer, rewind and try that again. To me, putting all the numbers in at one time instead of solving it individually is a time saver, and it also keeps you from making mistakes. So rewind and try my method again if you didn't get that answer. And when you're practicing, I encourage you to enter all the numbers in at once. All right, last thing we want to talk about is something called Dalton's Law of Partial Pressure. And so Dalton's Law of Partial Pressure says that the total pressure of a gas mixture is the sum of all of the partial pressures of each of the gas components. And so we use a capital P for pressure, and then to indicate pressure of what, we use a subscript of usually the formula for the gas. So this generic equation, P total is equal to the partial pressure of A plus the partial pressure of B plus the partial pressure of C. And so we can work through a problem where we see we have a sample of exhaled air contains 4 gases with the following partial pressures. Nitrogen has a pressure of 563 millimeters of mercury, oxygen 118 millimeters of mercury, carbon dioxide 30 millimeters of mercury, and water 50 millimeters of mercury. What is the total pressure of this sample? So P total is going to be equal to the partial pressures of each individual part of this sample. So we have the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of carbon dioxide plus the partial pressure of water. And so to solve, we're just going to plug in our numbers. So we have 563 plus 118 plus 30 plus 50. And if we put that in our calculator, we see that we have 761 millimeters of mercury. So that's a very easy equation. You just add the partial pressures together and to get the total pressure. All right, that does it for part 1 of chapter 7.